All right, we're going to continue with acids. I started phosphoric acid, but we'll just take a step back and look at the acids in general. When we're looking at acids and looking at the equilibria, then for monoprotic acids, we only have two equilibria that we have to worry about. You know, there's going to be Ka for the acid hydrolysis and Kw. But when we deal with the polyprotic acids like phosphoric acid we were dealing with earlier, then we're going to have multiple Ks. Usually we break it down. Ka1 would be for the first proton, Ka2 for the second, etc. Depends on how many protons and Kw. What we try to do with all of these is we try to solve them stepwise. And so the approach to these stepwise, the stepwise works if the K's follow this pattern. For example, K for step 1 is much bigger than K for step 2, is much bigger than 3, etc. Depends on how many steps. Then if we see the K's follow this type of pattern where each successive K is much smaller than the previous one, then it works. Stepwise generally works. But if the steps have similar K's, let's say K1 and K2 are quite close, then typically these must be simultaneously solved. So we can get an idea by looking at the K values for the acids. So let's take a look at some K values. Now this is from Appendix D. Appendix D has a more comprehensive list of Ka's, acid ionization or acid dissociation or ionization constant. And so if we look at acetic acid is a monoprotic acid. We'd have Ka and Kw. If you look at Ka, it's 10 to the minus 5. What is Kw? 10 to the minus 14. Kw is 1.0 times 10 to the minus 14. And so 10 to the minus 5 to 10 to the minus 14 stepwise should be no problem, you know, because there's significant difference here. And so looking at these, acrylic is monoprotic. Now arsenic would be a triprotic acid here. And so if we look at arsenic acid, you know, the first step, we would solve these stepwise starting with the biggest K. And so looking at the biggest K here would be 10 to the minus 3. And then the next biggest would be 10 to the minus 7. That's 4 orders of magnitude. And the next K after that is 10 to the minus 12. Another 5 orders of magnitude, followed by Kw. Kw is 10 to the minus 14. So what we see is the successive pattern of decreasing Ks by orders of magnitude. And so this should be stepwise, shouldn't be a problem here. And so looking at the K values, it looks as if stepwise should be okay for most of the acids. In fact, all the acids, practically, are going to work, solving them stepwise, except for a limited number. And so this is why the book is going to focus on stepwise, you know, solution to multiple equilibria. As we go down, though, take a look at citric acid. Citric acid is a triprotic acid. Take a look at step 1. Step 1 would be the biggest K. We always start with the biggest K and then work our way down because the biggest K will have the most significant amount of reaction. And so looking at the biggest K here, it's 10 to the minus 4. That's step 1. But take a look at step 2. Step 2 is 10 to the minus 5. So we have a 10 to the minus 4, 10 to the minus 5. Both these steps probably are going to be comparable in terms of contribution. Now, what do I mean by contribution? Well, in acid solutions, we're looking at hydronium-producing steps. In base solution, we'd be looking for hydroxides. We'll talk hydroxide-producing steps. We'll talk about bases later. And so the K value is going to tell us, about how much hydronium will be generated. And so if we're looking at this strong acid, strong acids are strong electrolytes. Strong electrolytes ionize 100% or hydrolyze 100%. And so an example of the strong acid, let's talk about this, would be HCl. When we look at the K value for HCl, it just says very large. In fact, when we look at the K value for all strong acids, it says very large. And so what this means is this. For something like HCl, we expect 100% reaction. That is, this is going to form hydronium plus chloride, and we'll have 100% reaction. Well, when we're dealing with acid hydrolysis like this, we also call this 100% hydrolysis. Or we call this 100% ionization. Although technically it's not really an ionization, it's a hydrolysis. It's reacting with water. In other words, this is a one-way reaction. It just goes forward 100%. Now for weak acids, K is small. If we have a K is small, for example, like acetic acid, HC2H3O2, when it hydrolyzes water, it's not going to be a 100% reaction. It's going to form some hydronium and some acetate, depending on how big K is. Ka for acetic acid is 1.8 times 10 to the minus 5. And so this is going to result in about roughly 0.1% hydrolysis. But our book uses the term ionization, so I'm going to use that same thing. It's about 0.1% reacted or 0.1% ionized, so 0.1% ionization. In fact, the higher the percent ionization, the stronger the acid. The higher the percent ionization, the stronger the acid. And so by looking at the K value, we can get an idea of how strong the acid is. And so we look at acetic acid. Acetic acid is 1.8 times 10 to the minus 5. Acrylic acid, is that a stronger acid or a weaker acid than acetic? Well, acrylic acid is 5.5 times 10 to the minus 5. And so the first thing I'd say is they're about comparable, because both of them are going to have a K value around 10 to the minus 5. Acrylic acid would just be a hair stronger, just a tiny bit stronger, because it's 5.5 rather than 1.8. If we go on to arsenic acid is orders of magnitude stronger, because it's 10 to the minus 3. So this is going to generate a lot more hydronium. But if we look at arsenic acid is actually a triprotic acid. And so when we look at the hydronium that's generated, we're going to generate most of the hydronium in the first step, because the first step is 10 to the minus 3. If we go to the second step here, the second step is 10 to the minus 7. With a K value of 10 to the minus 7, we aren't going to get nearly as much reaction. And so we won't get that much. So we're going to generate more hydronium overall, but most of it's going to come from the first step. If we look at arsenic acid is 10 to the minus 10, which is a very weak acid. This one is. Hydrocyanic acid, which we looked at the other day. Let's take a look. Is also a 10 to the minus 10. Very weak acid here. So we don't generate much. But still, this is orders of magnitude bigger than water. Water is 10 to the minus 14, so we'd still do this stepwise. We do this one with the biggest K first as a monoprotic, then we do KW. We try to do it in steps, step 1, step 2, or something like that. All right, so we take a look at, since we're on this chart, let's take a look at what the K values range from. What's the biggest K value that you see? What's the smallest K value that you see on this chart? So let's take a look at some of the K values here. All right, the biggest K values that I see would be something like this: sulfuric acid. Sulfuric acid is a strong acid. They don't even show the K value because the K value is very large, so it's not written there. Selenic acid, very large. Right? At least the selenic acid is a diprotic acid like sulfuric acid. So it's very large here. The Ka2s here are kind of big as well, 10 to the minus 2. Where's HCl? HBr, HI, where are the other ones? HNO3. Why are they missing from this chart? Why do they only show me sulfuric? What happened to the other 6 that you guys memorized? Those are all monoprotic, right? All the 6 other strong acids you memorize are monoprotic. And they figure, why waste the space? All they're going to do is write HCl and or strong acid or very large. And so they expect you to memorize it. That doesn't mean that people memorize it because, on tests, I'll put an acid like HCl and I won't give the K value. And then somebody during the exam is going to come up to me and ask me, how can I solve this? You didn't give us the K value for HCl. Well, yeah, I purposely didn't give you the K value because I expect everyone to have those memorized. Right? Strong acid going to be there. And so the biggest are very large. What's the smallest K value that you see here? Yeah, the smallest one is for this, hydrogen sulfide ion. And what's unique about this is this, 10 to the negative 19, which means HS minus is a weaker acid than water. Water has a K value of 10 to the minus 14. That means water produces more hydronium than HS minus would. And so anything smaller than 10 to the minus 14 is weaker than water. Well, when we look at this chart, there's only one thing smaller than 10 to the minus 14. Everything else is stronger than water. The only thing that's weaker is this one, which means that the sequence of steps is going to be interesting for something like H2S, which we'll look at in a moment. And so this. Even though when we're talking about the Ks, as the Ks get smaller, the contribution decreases. The hydronium ion contribution to the acid solution decreases. They become less significant. But the most important thing here is to check that the stepwise succeeds or to check if it fails. How can you tell if the stepwise fails? Here you're just looking at, well, it should work, but you aren't 100% sure. The way you're going to check if stepwise fails is by determining if each successive step perturbs the previous step. And so how can you tell if stepwise fails? Well, here, if the, what should we say? If the current step does not perturb the previous step, significantly, then stepwise is okay. We'll look at an example of this a little bit later. If the current step perturbs the previous step significantly, then stepwise fails. And so this is the whole strategy behind the Ks, because if the Ks are getting smaller by orders of magnitude, then the reaction is becoming less and less significant, and therefore it shouldn't perturb the previous step as much, if at all. Whereas over here, when we look at citric acid, if we're currently on step 2, and step 2 has a 10 to the minus 5 K, and step 1 is the 10 to the minus 4, then it's likely that step 2 will perturb step 1 because of the comparable Ks. In other words, both steps are significant. I think on the last test, I'm not sure, but there are some acids, if you dig around, there are some acids with a K for step 1 at 10 to the minus 5 and a K for step 2 at 10 to the minus 5. And so both steps are quite significant. All right. So let's do calculation then. We're going to start off with the triprotic acid because, when we do acids, whether they're polyprotic or monoprotic, it's always the same method. And so this is what we left off with last time, right? Did we leave off with this? But we didn't start this at all? Oh, okay. I thought we did, but I guess we're... All right, let me talk about phosphoric acid then. Phosphoric acid has 3 acidic hydrogens. So there's going to be a Ka for step 1, a Ka for step 2, and a Ka for step 3 just from phosphoric acid. And those steps are going to be like this: H3PO4 plus water, which will lead to hydronium and dihydrogen phosphate. This we call Ka1 for phosphoric acid. Ka1 for phosphoric acid is also just Ka for phosphoric acid. Okay, then we have another proton that can hydrolyze water. And so if H2PO4 minus collides with the water, we'll form hydronium and monohydrogen phosphate. Okay, we call this Ka2 for phosphoric acid. It's just the second ionization step or the second hydrolysis step. This is just the Ka for dihydrogen phosphate. We can put some numbers on this. When we look at phosphoric acid, first step is 7.1 times 10 to the minus 3. 7.1 times 10 to the minus 3. Second step for phosphoric is 6.3 times 10 to the minus 8. That's 5 orders of magnitude difference. This should work stepwise. We should be okay. Let's go on. Monohydrogen phosphate can lose a proton to water as well. And this is going to form hydronium plus phosphate. And so what we did was we looked at, this is an acid solution. So we look at all the hydronium formers in acid here. We have 3 of them. This would be Ka3 for phosphoric acid, and Ka for monohydrogen phosphate. And let's look at the value here.
4.2 times 10 to the negative 13.
Yeah. Look at that. 4.2 times 10 to the negative 13 is another 5 orders of magnitude. And so each successive step is becoming less and less significant. And therefore, there's a good chance that each successive step won't perturb the previous step. If the K values are close, then we got to worry about it, having to solve this simultaneously. All right, and then there's one more hydronium ion contributor, and that would be water colliding with water. We can't stop these collisions. Water is just going to collide with itself to form some hydronium and hydroxide. And this would be Kw. Kw is 1.0 times 10 to the minus 14. And so it's also small. Although it's not a big drop here, it's already successive enough. If we only had 2 steps, one step was 10 to the minus 13 and the next step is 10 to the minus 14, then it's probably simultaneous, right? If there are only 2 steps. If we eliminated the first 2 and we just had these last 2, then it's simultaneous. But since we have these successions, it's going to be stepwise, it's looking like. But some people will say, well, that's good. Stepwise is good because we don't have to solve 4. Can you imagine solving 4 equations simultaneously? What a headache that would be. That would be very difficult. It'd be very difficult. That's why I didn't mention this earlier, or did I? Did I mention about Visual Mintech? No. That's why there are programs like Visual Mintech that solve these simultaneously for you. You don't have to do it yourself. In fact, we're going to do a Visual Mintech lab. And the Visual Mintech is much more powerful because Visual Mintech uses activities. They don't use the concentrations. And they account for ion pairing as well, and all the species that are generated from that. There's a Visual Mintech lab which is going to come later after we finish chapter 18. So we're going to look at those calculations. And so stepwise is going to be a heck of a lot easier than solving these 4 equilibria simultaneously. But some people might say, maybe we can combine these first 3. And so what about combine? And so stepwise looks good. So stepwise looks good. But what about combine? There are going to be 3 ways that we're going to solve multiple equilibria. The 3 ways are going to be stepwise, which is our preferred method, simultaneous, which we want to avoid, if at all possible, and combined. Now, combined seems like the way to go for this, for sure. Combined, because, what if I add these 3 equations? If I add these first 3 equations, what do I do with the K values? This is like Hess's law, but not like Hess's law. If I add these three equations here, then I multiply the K values, right? This is chapter 15. And so what I'm going to do is I'm going to sum up the first three steps. 1 through 3. If I sum up steps 1 through 3, the net equation I have is H3PO4 plus 3 water yields 3 hydroniums plus a phosphate. And then K for the combined, or K for the sum of the steps is just equal to Ka1 times Ka2 times Ka3. And so what I did was, I'm just going to save a lot of work because I don't have to do any ice tables for these. There would be 3 ice tables we'd have to do for this if we're going to solve this stepwise, like we did for HCl, HCN earlier. HCN turned out to be simultaneous. How does this look? This looks perfectly fine according to chapter 15, right? There's nothing wrong with this. But there's something wrong with it, because even though mathematically it works, the thing that doesn't work is physically, this doesn't work. And the problem with this is mass balance. Back in like Chem 4, you learned that mass, conservation of mass, you remember that law? Conservation of mass just means that atoms are neither created nor destroyed. Well, in this case, we're missing stuff. There are missing species. Important missing species. When we look at this equation here, there are only 2 phosphorus-containing species. H3PO4 and PO4 3- are the only phosphorus-containing species. But when we look at the most significant step, what's the most significant step? The first step here, because it has the largest K. And the first step generates what? H2PO4-. And so we expect H2PO4- to be in the greatest abundance. Actually, this is weak acid. Weak acid, the unionized molecule should be. And so we should have unionized molecules of phosphor followed by dihydrogen phosphate. Dihydrogen phosphate should be the next most abundant species after phosphoric acid because it's got the biggest K, right? When we get all the way down here, how much phosphate do we expect? Do we expect much phosphate? Not with a 10 to the minus 13 K value. The 10 to the minus 13 is very small, so we don't expect that much phosphate. But when we look up at this, where's our dihydrogen phosphate? Not only that, we expect more monohydrogen phosphate than phosphate. And so where's our monohydrogen phosphate and our dihydrogen phosphate? Missing dihydrogen phosphate and monohydrogen phosphate. And so this is what we mean by mass balance. All the grams of phosphorus don't end up in 2 species. The grams of phosphorus ends up in a multiple. If I have, let's say I had 10 grams of phosphorus altogether, then I do expect, a certain number of grams present here, a certain number of grams present here, etc. But over here, if I have 10 grams of phosphorus, I have to split it up between only 2 species. That's a mass balance problem. We've lost some matter. Does that make sense? And we gained, gained extra. of this. The actual amount of phosphate is going to be very small, so you know all the phosphorus is going to end up here, meaning that we've lost those two. Okay. And so we're missing some stuff. And so combine fails. In general, combine fails because of mass balance, except under restrictive circumstances. It works for a small number of problems found in chapter 18. Under a certain set of conditions, you know, for example, under a certain set of conditions, these, you know, intermediate species that get canceled out are negligible in terms of their concentration, so we can just kind of ignore them. And there won't be a mass balance problem. But we'll see that in chapter 18. So when you look at Petrucci, Petrucci is just going to solve everything stepwise, basically, because most things work, and there are a few exceptions.
Does that mean you have to do ice chart for each?
Yeah, every single step. And so let's do that. This is why we look for ways to shortcut the process, but in this case, we can't. I mean, combine would have saved us a lot of work, but it's not going to work for this. So let's go ahead and do phosphoric acid. Step one, we always start off with the biggest K and then just work our way down. The biggest K is going to be Ka1 for phosphoric acid. The equation for Ka1 is just the first hydrolysis step or first ionization step here. This is going to produce hydronium and dihydrogen phosphate. Ka1 is 7.1 times 10 to the minus 3. This is just going to equal the hydronium ion concentration times the dihydrogen phosphate concentration divided by the phosphoric acid molecule concentration. This is a weak acid, so weak acid is only partially ionized or partially hydrolyzed water. And so we should have not all of our phosphoric acid ionized. So what we're going to do is we're just going to assume that none of the phosphoric acid molecules have hydrolyzed. In other words, we reset this to left. We have to reset this to the left because we don't know what these values are anyway, you know, at equilibrium. If I have a beaker of phosphoric acid, it's already hydrolyzed. Well, we just imagine nothing's happened, and then we'll lose some. Weak acids will lose a little bit, right? Like acetic acid. What did I tell you what acetic acid's percent ionization is? No. I wrote it. Did I write it down? No. For the weak acid example?
What's acetic acid?
Okay, acetic acid, that K translates to about 0.1% ionization. So just go ahead and write that down. Well, you know, I don't know what this is going to translate into. And so the reason I like, this is the reason why I like 0.100. Because is 100 molar possible, you think? No. I mean, if somebody asked you to make 100 molar phosphoric acid, it'd be pretty next to impossible to do that. But 0.100 is, and the reason I like 0.100 is because it's so easy to calculate the percent reaction or the percent ionization because we can just see it right off. So this is going to be 0.100 minus x. This is going to be x molar. This is going to be x molar. And then we just solve this over here. This is going to be x squared over 0.100 minus x. Then, although this is not so bad, just a quadratic, I go ahead and use a simplifying assumption, because if it works, we save time. So some people mention the rule of 100. Have you heard of that? Or the rule of 1,000? I don't usually bother with that. The reason I don't bother with that is because it depends if you have something called common ion, which we'll talk about, or not. And I just go ahead and do it. It doesn't take that much time. And so we'll do 0.100, which means that x is equal to the square root of 7.1 times 10 to the minus 2. X is 0.0266, so this is why I like 0.100, because this would be a 26.6% change. 26.6% change, or, we call that percent reaction, because we're losing that out of 100, or we call it percent ionization. Is that okay for the simplifying assumption? No, the percent change has to be less than 5%. And so this is greater than 5%, and therefore the simplifying assumption fails. But, it didn't take that much time. It was worth trying. And so what we have to do is we have to solve this. And so what we're going to do is we're just going to get it into quadratic form. So this is going to be x squared plus 7.1 times 10 to the minus 3x minus 7.1 times 10 to the minus this 0.1, so 10 to the minus 1, 10 to the minus 3 is 10 to the minus 4 is equal to 0. Is that right? So did anybody buy the quadratic calculator? You got it? So you could just punch in the numbers. This is what I do, since I bought 3 of those, which I've lost. So I need to buy a new one. But when I do the homework, since you can have a computer available, I just bring up a quadratic solver webpage. There's lots of these on the internet. And then I'll just plug in A is 1, B is 7.1 e to the minus 3, and C is minus 7.1 e to the minus 4.
We can't use this.
You can't use this on the test. You're going to have to use the quadratic formula on the test. But on your homework, you can use it. It saves you time. But you don't get to practice the quadratic formula. So you should solve some of them by hand until you feel pretty comfortable with them. And so we get 2 roots for this. A negative, it can't be negative. We can't have negative molarities here. So it's got to be the positive. And so it's 0.0233. It's fine. We're close. We got 0.0266. X is 0.0233. And so going back and calculating the concentrations, well, 0.100 minus 0.0233. This is a 23.3% change, or 23.3% ionization, or 23.3% hydrolysis. But wait a minute, 23.3% is too big, isn't it? But it's no problem. It is a 23.3% change because we didn't use any kind of assumption here. We just calculated the actual percent. And so that means we're going to be left over with 0.0767. So 76.7% of the phosphoric acid remains as molecules, in the form of molecules. The signs switched. The signs are switched because I multiplied this on this side and then added and subtracted. And so the signs are switched. And so this 0.1 times 7.
The X.
Yeah, 7.1. It should be negative, but what I did was I multiplied this and then added to both sides. And I moved it, and so that's why the sign changed. I just skipped a couple of steps.
So what's the reasoning behind us being able to cancel out that X?
Cancel out this X right here. To if this worked, then we wouldn't have to use the quadratic formula. We just use the square root key on the calculator. If this worked, and so it's just to save time. There's no other reason other than to save time because by ignoring this X here, you're introducing an error in the calculation. As long as the error is small, we'll live with it because saving that amount of time is a lot better than having to calculate the quadratic equation or by hand. You know, you do these. Minus B, you know, plus or minus, you know, whatever. It becomes a hassle. All right, so the hydronium over here is going to come out to 0.0233 molar. And the dihydrogen phosphate is going to come out to 0.0233 molar. Yeah. And then what we'll do is we're going to double check our K to make sure we didn't make any errors. And so the double check is we'll take these concentrations and make sure that they multiply out to 7.1 times 10 to the minus 3. And so can you do that? 0.0233 squared divided by 0.0767. I don't like to round these numbers yet because that really screws up my K. And so when I double check it, adds uncertainty if it's a round off error or a calculation error. What does it come out to? 7.07 times 10 to the negative 3. Is that close enough? Yeah, this round, so it's good. This is good. You know, the reason it's different is because we didn't carry all the digits. If we carried all the digits in our calculator, then it would have come out to 7.1. All right, what's going to happen here is this is the end of the line for the phosphoric acid. So the phosphoric acid molecule concentration is, you know, most of the molecules stay intact. Just 23.3% of them ionize to form hydronium dihydrogen phosphate, but hydronium dihydrogen phosphate continue on in step 2. And so what we're going to do is we're going to bring these down to the next step. What is the next step? So we go to step 2. Step 2 is the next biggest K. The next biggest K is the dihydrogen phosphate hydrolyzing water. Hydronium and monohydrogen phosphate. This is Ka2, which was 6.3 times 10 to the minus 8. This is going hydronium ion concentration times the monohydrogen phosphate or the dihydrogen phosphate. Okay, this will be the next biggest hydronium ion contributor to this. And so the initial here is going to come from step 1. From step 1, we have 0.0233 molar dihydrogen phosphate. And the hydronium is not going to be 0. The hydronium is from step 1, 0.0233 molar. And so both of these initials are from step 1. But from step 2, we assume nothing's happened. If nothing's happened, it should be 0 molar for the monohydrogen phosphate. So we're going to assume that no dihydrogen phosphate has collided yet. And then we're going to allow it to react. And so the dihydrogen phosphate collides with water to generate some hydronium and monohydrogen phosphate. And so we're going to lose some dihydrogen phosphate as minus X. We're going to gain some hydronium as plus X and gain some monohydrogen phosphate as plus X. And so at equilibrium, I'm going to have 0.0233 minus X, and then 0.0233 plus X molar, and then X molar. Okay, so we need to solve for X. Solve for X. We have 0.0233 plus X times X divided by 0.0233 minus X. Now, X is going to be unusually small here. The reason X is going to be unusually small is because of the common ion effect. We have a lot of hydronium here to begin with. And the hydronium is going to attack any monohydrogen phosphate that's formed. And so this is like the predator-prey type deal I was talking about earlier. You know, having a lot of hydronium here is going to keep the population of monohydrogen phosphate from growing too big. And therefore, X cannot grow as big as it normally would. So for example, if hydronium were 0 to begin with, then X would be a lot bigger. But because of the common ion effect here, X is going to be smaller. Well, that's good for a simplifying assumption, because a simplifying assumption, we want a small X, we want a small change, right? And so in common ion problems, this is why I don't really pay attention to the rule of 100, because in common ion problems, you know, even if it fails the rule of 100, it still might work depending on how much common ion you have, how much, you know, if you got a lot of prey here, oh well, anyway, it could change the dynamics of this, even though you do look at your initial. And so here, we're going to go ahead and try the simplifying assumption. And we get 0.0233 plus X just gives us 0.0233, and then that's times X. 0.0233 minus X just gives us 0.0233. 0.0233's cancel, and then we get this, that X is equal to K. X is equal to K. This is something that Petrucci mentions. You know, when we have a polyprotic acid, usually in step 2, X is equal to K. But you have to keep in mind, it only works if the simplifying assumption works. If the simplifying assumption doesn't work, then X is not equal to K2. And so I'm just going to throw that out there because Petrucci mentions that. And so if the simplifying assumption, well, let's see if it works. Actually, I don't know if it will work because we need to check it. And so what is the percent change here? Percent change would be 6.3 times 10 to the minus 8 divided by 0.0233 times 100%. It's going to give us what? Actually, we don't really have to do this calculation. It's going to be 10 to the minus 8 times 10 squared is 10 to the minus 6 divided by 10 to the minus 2. Bring that up. It's going to be about 10 to the minus 4% change. 10 to the minus 4% is going to be much smaller than 5%. And so the simplifying assumption worked. And therefore, x is equal to Ka2 for step 2. I don't know if that's worth memorizing or not. I don't think so. Well, the simplifying assumption, well, that, you know, when you see a percent change like this, 10 to the minus 4%, that's good. You know, even though we're introducing an error, we're introducing an error by ignoring this. But I'll tell you, if we solve this using the quadratic formula, we would get the same x. X would come out to this. You know, maybe the 6th digit out here is different, or the 5th digit out here is different, but, you know, that's negligible. And so the simplifying assumption should work quite well here. In other words, this should be a negligible change. So let's take a look. It's 0.0233 minus x. X is going to be 7 zeros and a 6 3. So 1, 2, 3, 4, 5, 6, 7, and then 6 3. So add some zeros here. So this is going to be 0.0232. 999 dot molar. And so we went from 0.023 to 0.023299999. Was there much change? No. This was what we call an insignificant change here. Then over here, this is equal to 0.0233 plus I need 7 zeros. Then a 6 3. Need to add 2 more zeros here. We get 0.023300063 molar. Was that much of a change? We added this tiny bit, the 63 way out here. No, this is what we, again, negligible change here. And then, oh, what about this? Is this a negligible change here? No, this is a significant change. And so this is going to equal 6.3 times 10 to the minus 8 molar. And compared to 0, that's significant. Well, let's just make sure that we didn't screw up our calculation by double checking our K value here. Let's see if it works out. What does it come out to?
6.3 times 10 to
6.3. Give me one more digit. 3 0. Times 10 minus 8. So we're good. That works out. It works out well. All right, but we have to check something. We have to make sure that the current step did not perturb the previous step. So what we see here is that the concentration of dihydrogen phosphate and the concentration of hydronium did change. The hydronium went up, the dihydrogen phosphate went down. So we lost a little bit of dihydrogen phosphate and we gained a little bit more hydronium. Did that perturb this? The way we see if it perturbed is now the new dihydrogen phosphate concentration is this. So we plug that in here. The new hydronium concentration is this. We plug that in here. We double check it. Is it still going to? Yeah, this was a negligible change, right? And therefore, if it's a negligible change, it does not perturb the previous step. And so this step, all right, we'll just say step 2 does not perturb step 1. we had negligible change. Well, we had negligible change for these two, but there was a significant change for this last one. But this last one is not part of step one, so we're okay. Which gives us, people are always looking for, shortcuts or ways we can speed things up. And so one of the things is this: if you're calculating pH measures the total hydronium concentration in solution. When we look at phosphoric acid, there are going to be 4 hydronium ion contributors corresponding to the 4 steps. But we see something already. We see that practically all the hydronium is going to be generated in step 1. If we look at step 2, did we get much additional hydronium? No. We didn't get much additional hydronium because of 2 reasons. 1, the K is small. And 2, the common ion effect. The common ion effect means that we can't generate much hydronium because that will attack any monohydrogen phosphate that's being formed. And so, based on those 2 reasons, if you want the pH of phosphoric acid, all you need to do is step 1, and you could skip steps 2 through 4. Right?
Is it only for this case?
Well, let's look at that in more detail. And so let's look at pH calculations. For pH calculations, most polyprotic acids step 1 only is required. We can ignore the rest because those contribute a negligible amount of additional hydronium. For monoprotic acids, we just do step 1, ignore Kw, is Kw usually is a negligible contributor of hydronium. That works when we're looking at scenarios like this, Arsenic acid, would it work? Yeah, it should have worked because in step 1 is 10 to the minus 3. We should generate most of our hydronium there. In step 2, it goes down to 10 to the minus 7, 4 orders of magnitude smaller. Because of this small K and the common ion effect, we expect very little additional hydronium. And so for arsenic, step 1. Arsenous acid is a monoprotic acid. Step 1 would be 10 to the minus 10. Step 2 would be Kw. Kw is 10 to the minus 14. 10 to the minus 10 versus 10 to the minus 14? Probably just step 1. The only exception for that is very dilute solutions. In monoprotic, except for very dilute solutions. The example was HCl. Remember HCl? Step 1, K is very large. Step 2, K is 10 to the minus 14. But most of the hydronium came from step 2 because it was almost pure water. There's so little acid in there. It's essentially like pure water. And so we got to be careful of that. The other case is where we have both, you know, low concentration, small k, like HCN. Remember, for HCN, it was, what was it, 1.0 times 10 to the minus 5 molar HCN. We couldn't ignore step 2 for this. All right, so let's go on here. For pH calculations for benzoic, no problem. Step 1, as long as the concentration's high enough, should be it. These are fine. Citric acid, though, take a look at this. Step 1 is 10 to the minus 4, step 2 is 10 to the minus 5. So is step 2 a much smaller contributor? Not really. Step 2 is almost comparable to step 1. The only thing going for us is the common ion effect. And so this is a borderline case. Because of the common ion effect, you know, we might be able to ignore step 2, but because of the large K, we probably should factor step 2 in. If we look at sulfuric acid, step 1, very large. Step 2 is 10 to the minus 2. So going from very large to 10 to the minus 2, their orders of magnitude different. But what we have to do is we have to also pay attention to the order of magnitude here. And so for polyprotic acids, erase this. Let me put this in parentheses here. For polyprotic, is the magnitude of K2 is, you know, 10 to the minus 1, 10 to the minus 2, maybe 10 to the minus 3, you know, we'll say 10 to the minus 2. Then step 2 is significant. It's just because the K is kind of big. Since the K is kind of big, then it's going to be a contributor no matter how big step 1 is. And so sulfuric acid, for sure, most of the hydronium is going to come from step 1, but there's also going to be a significant amount of hydronium from step 2, because think about this. Hydrogen sulfate is like 1,000 times stronger acid than acetic acid. Acetic acid is 10 to the minus 5, hydrogen sulfate ions 10 to the minus 2. And so that's a big K, you know, 1,000 times stronger than acetic. And so when we have a step 2 that has a kind of a large K value, then it's going to be a significant contributor. And to give you an example, sulfuric acid, about 90% of the hydronium in solution comes from step 1, and about 10% of the hydronium comes from step 2. And then Kw would be negligible. Here, Kw is only 10 to the minus 14. If we look at sulfurous acid here, sulfurous acid, I would just do step 1. Because if you look at sulfurous acid, the first step is 1.3 times 10 to the minus 2. It was big, so we're going to get quite a bit of hydronium from that, more than we got from phosphoric acid. But when you go down to step 2, it's 10 to the minus 8, 6 orders of magnitude smaller. And so for step 2, I would completely ignore it. For selenic acid, would you ignore step 2 for pH calculation or factor in step 2? You got to factor in. I mean, selenic acid is 10 to the minus 2 for step 2. You got to. That's going to be a significant contributor. Let's take a look at another one. For pyrophosphoric acid, pyrophosphoric is kind of interesting because this is not a triprotic, this is actually a tetraprotic. So there'd be 5 steps here, including Kw. But for pyrophoric, if I just want the pH, how many steps do I need to do? Well, you look at the first step is 10 to the minus 2, and then this next step is 10 to the minus 3. I'd probably do the first 2 at least. And then the third step is 10 to the minus 7. I'd probably ignore that. for pH calculation. For malonic acid, the first step is 10 to the minus 3, second step is 10 to the minus 6. If you want a pH calculation, just step 1's enough for malonic acid. So that saves time. So sometimes you're just asked for the pH. If I was just asked for the pH, I wouldn't have even bothered with step 2 here. And step 1 was 10 to the minus 3, step 2 is 10 to the minus 8. Forget about step 2. You know, the bulk of the hydronium is going to come from step 1. And we calculated, if we added the additional hydronium from step 2, the 63, it would have made no difference in our pH calculation. But we aren't after just pH here. We want more. In fact, we want to know something called the solution inventory. The solution inventory are what are all the species present in a beaker of 0.100 molar phosphoric acid. And so this is why we're going to go through all the steps. And so we're going to go to step 3. And so it turns out that dihydrogen phosphate is not involved in step 3, so this is where dihydrogen phosphate stops. And so this will be the final concentration of dihydrogen phosphate. But this is not the final concentration of hydronium, because in step 3, we're going to get additional hydronium. And this is not the final concentration of monohydrogen phosphate, because in step 3, monohydrogen phosphate is going to hydrolyze with water. And so we have to carry those down. And so step 3 would be the next biggest K. The next biggest K is 10 to the minus 13, which corresponds to monohydrogen phosphate hydrolyzing water to form some hydronium and phosphate here. K83 for this is 4.2 times 10 to the minus 13, which is going to equal the hydronium ion concentration times the phosphate concentration divided by the monohydrogen phosphate concentration. And so carrying down the monohydrogen phosphate from the previous step, we add 6.3 times 10 to the minus 8 molar. The hydronium from the previous step is 0.0233 ... molar. And we're going to assume this is reset, like nothing's happened, no collisions yet. Okay, then we're going to go ahead and allow this to react. And so we're going to lose a little bit of monohydrogen, which is going to increase the hydronium a little bit and increase the phosphate a bit. And so at equilibrium, we have 6.3 times 10 to the minus 8 minus x, 0.0233 plus x, and x. So in a problem like this, can we use this thing, x is equal to k here? You might see x is equal to k in the book, but it doesn't work for everything. In this case, it wouldn't work, even if we use the simplifying assumption. Let's go ahead and see what we end up with. 0.0233 ... plus x times x divided by 6.3 times 10 to the minus 8 minus x. When we use the simplifying assumption, these don't cancel out and we don't get x is equal to Ka3. It doesn't work. Just work for step 2. Again, I'm just bringing this up because the book does. But what we have to do is we have to do a calculation. But we always look for shortcuts or tricks. So one will be the simplifying assumption. Now, the simplifying assumption looks like it's good for this because this is kind of a big number and x hopefully is small. And so 0.0233 plus x should be about 0.0233. And then this will be times x. And so this would be the analogy. If I have a swimming pool and I add a drop of water, the volume didn't change really. But the thing is, this might be a swimming pool, but this is like a few drops of water. If you have a few drops of water and you remove one drop, then that's significant, right? And so what you could do is you could do a selective, not successive, a selective SA, that is simplifying assumption. So for example, we could do the simplifying assumption on the numerator, but leave the denominator as is, because it might not work, right? But you know what? I don't want to think about this, and I don't want to think about the rule of 100. I don't want to think about any of that. You know why? Because it's so quick just to do it and see if it works or it doesn't. And so even though, I'm starting to worry about the rule of 100 here, I'm not. I'm just going to try it. If it fails, it fails, right? If it works, it works. So let's do it. And then what do we get as our x? X is equal to 1.13. Is that what it is? Times 10 to the negative 18?
No,
8? Is that what?
It's 18.
Times 10 to the negative 18? So I was worried about this, this in the denominator, but let's calculate the percent change. The biggest percent change is going to be x compared to this. And so that'll be x over 6.3 times 10 to the minus 8 times 100%. We'll just do it by orders of magnitude. So this is 10 to the minus 18. That'll give us 10 to the minus 10. And this will be about 10 to the minus 8% change. And 10 to the minus 8% change, in fact, the simplifying assumption worked very well for this. Actually, this would have passed the rule of 100 or whatever. So we didn't have to do a selective assay. And so no problem here, that worked. And so how much monohydrogen phosphate do we lose? Well, we only lose about 10 to the minus 8% of it. That's a very small change. And so we started off with 6.3 times 10 to the minus 8. So that's 1, 2, 3, 4, 5, 6, 7 zeros and a 6, 3. And then we're going to lose, now that's 18. So I need 17 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, and a 1, 1, 3. And then we get to add some zeros here. And so this is going to come out to 0.007 zeros and a 6299999. Actually, plug this into your calculator, and what do you get?
6.3.
Uh-huh.
I don't think that number's correct. Shouldn't it be times 10 to the negative 7? For the x?
For the x?
Yeah.
This one?
Yeah.
Let's check it. We can just look by order of magnitude. So this is 10 to the minus 13, 10 to the minus 8.
10 to the negative second minus 10 to the negative 8, which is 10 to the 6 times 10 to the negative 13 is 10 to the negative 7.
Okay, so this is 10 to the minus 2 divided by 10 to the minus 8. And we bring the 10 to the minus 8 above and change the sign. So 10 to the minus 2, so minus 2 plus 8 would be plus 6. And then divided by both sides. And so 10 to the plus 6, and that's going to give us 10 to the negative 19. So this is about right. Yeah, it would be, this should be around 10 to the minus, oh, actually, no. Yeah, 10 to the minus 19, 10 to the minus 18, in that range. That's what we expect, 10 to the minus 20. So order of magnitude looks okay. when you plug this number into your calculator, it's just gonna round it. You know, your calculator can't handle that many digits, so it'll just round it back to 0.0063. And so what we call that a negligible change.
On the exam, do we have to be that exact?
No. On the exam, I mean, call this 63. It'd just be a hair under 63, you know, but dot, 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 more. All right, here, this is going to be 0.0233 plus, okay, I need 17 zeros, right?